Hi, in this video, we want to take a look at vector generalized linear and additive models. All right, so what's going on here is that we have categorical data with more than two levels. Okay, so regular linear regression makes the assumption that your target variable is on a continuum. It's Gaussian distributed, it's on the bell curve. Now, if I'm doing logistic regression or probit regression, then we're making the assumption that we have two levels and we can represent our levels with zeros and ones. Okay. Well, what if we have something a little bit more interesting? What if we have the situation where I have categorical data and I've got more than two levels? How do I handle it? What do I do? Well, there's several different ways. So as a first go at this, we're going to go ahead and take a look at the VGAM package. So vector generalized additive model package in R. This is pretty much the standard for R to handle these types of problems. And we're going to build a few models looking at species of different plants. All right, so first thing we're going to do, we're going to load our data. Not surprising. So we're taking data from the package we want to use. Not surprising. So using the data function. Now, something I did, I wanted to organize my target variables. So remember, for this one, I have a bunch of target variables on this. Actually, I'm going to scroll down. So here, altitude is my one predictor variable. I have one predictor variable. The rest of these are target variables. And each of these corresponds to some kind of plant species. Now, information about the plant species, I don't know, I don't care. I've got data, I'm working with data. All right, so this is a species. So during a period of surveying, some area, people went out and they looked to see what plant species were in each area. And they recorded a 0 if the species was not there, a 1 if it was. All right, now, what we want to do, we want to use altitude to model the presence of these species, yes or no. Okay, so notice that I've got a lot of zeros going across, and eventually I get to a 1. So this is the only observation in this area was this species. This is in the first row observation in the first area. This was the only plant seen, and the altitude was at altitude 0. Okay. And then at altitude 0 was the next area, and we can see that this one is the only species located. All right, now we can keep on going through and looking at this. And now you'll eventually notice that, or if I keep on looking through, I'll find the case. Here it is. Here's a good one. At altitude 660, we have two different species in the same area. So this tells us that we do not, like those previous rows kind of would make us think that you could only have one species in an area. Here, we're in a situation where multiple species, potentially all of them, could be in a given surveyed area. All right, so now what I did, I went ahead and I wanted to organize my data just so I could understand it a little bit better, to see which target variables look like they have the strongest relationship with the predictor variable of altitude. So what I did was I looked at altitude and I put it into two groups for each target variable. So if it's a 0, that's a group. I put all the altitude with 0 for that target variable, and then I put all the altitude with 1 for that target variable. Then I did a pairwise t-test comparing the two, and then I sorted the columns by the p-values, and that's all the junk I did here. All right, so what I did was, you notice I took all the columns except for my predictor, which is altitude. So here, remember, this means does not equal. So I'm taking all of the columns that are target variables in the data set. Now here I'm doing pairwise t-tests. My group is the target variable under question. So for what the sapply function is doing, it's running over all of the different predictor variables for me, and this does this very quickly. A lot of computer programmers would want to do this in a for loop. This will be within R, for loops are slow. So I'm using sapply instead. Sapply and lapply are substantially faster than the apply functions. They're actually just souped up versions of, sorry, they're faster than for loops. They're actually really under the hood, just souped up versions of for loops, but they perform better. In general, in R, you want to avoid for loops. You want to vectorize everything as much as possible. All right, so when I do this, I sort everything out and then I just rearrange things. So, you know, I sort, actually, let me back up. This part here, after I do the pairwise t-test, it's going to give me the p-value. And so my alternative hypothesis by default is that we do not have equality. So it's a two-sided t-test. And so a p-value, what I'm trying to do, does it look like I have two different average altitudes for the two different groups? Okay. And then I sort everything. And so what this will do, the ones with the predictors with smaller p-value will be on the left, larger p-value will be on the right. So the ones that look like they have a stronger relationship with altitude will be the ones farther to the left. That way, I kind of have a feel for what's going on with my data as is. And then I sorted the columns just to make it a little bit easier to interpret. You'll notice that I go in reverse order, so I'm going from right to left. This way, with altitude on the left, it's the last one that gets sorted. And here's what the data looks like. So altitude is my predictor variable, and then the target variable that looks like it has the strongest relationship with altitude is this one, and the one that looks like it has the weakest relationship with altitude is this one. And these are all somewhere in between. And we can look at the summary. So here we can see, you know, what altitude is, and we can see for each of these target variables, we can, you know, see that they're all, the minimum is 0, maximum is 1 every single time. And using the mean, we can see that about 14% of the observations had this as it being present in the surveyed area, while here only about 6% of the areas had this species. So good for us to know. All right, so now let's go ahead and visualize the predictor variables. So remember, in this situation, I've got one predictor variable, and I've got a bunch of target variables in this setup. So keep in mind that really all of these zeros and ones are just coding of categorical data. And all these categories are actually my target variables. It's like we've taken linear regression, we completely turned it on its head. All right, so I want to visualize it, and ggplot likes something called tidy data. And tidy data means that I want everything formatted in a way, so however I'm going to visualize it, each row needs to be an observation. All right, so to be able to visualize this the way I want to for box plots, I need to make it so that each altitude and target variable value, individual value, is one observation for this. And so I need to put this, right now it's in wide format, I need to convert it to long format. And so I'm going to use the gather function. So in the tidyr package, if I have it wide, gather puts it like this and makes it long, like that. If I use the spread function, spread takes a long data set and makes it wide. All right, and I go ahead, I just do ggplot. And so here we can look through and we can see the box plot. So in this situation, the main thing I want to focus on is the relative position of the box plots to each other. If I see that the center boxes look like this, I am leaning towards believing that there is a substantial difference when altitude is considered. If they look like this, if the boxes are next to each other, I I'm leaning towards seeing that there's not a difference between them. Like altitude is not informative for this variable. So if I look here, I see that the boxes are knocking up against each other. And furthermore, the median lines are cutting each other's boxes. When the median lines are cutting each other's boxes like this, you're going to be like, well, there's not much of a difference based off of that. When I look over here, I can see that the boxes they're not completely off of each other, but they are lifted up. And I can see that the median lines do not slice each other's boxes. Therefore, I think I could probably get a decent logistic regression model off of this with altitude. Here, I don't think logistic regression with altitude will give you much information about this particular species. And then the rest of these are kind of somewhere in between. And since I ordered them, you can go down the line and you can see like the difference gets like weaker and weaker as you go from left to right. All right, so now let's build a generalized additive model. Now I'm going to do it with just one variable. And I'm going to do it with the one that looks like it has the strongest relationship because I want to build a good model. So what I'm going to do, I'm going to take the VGAM function from the VGAM package. And I'm just going to say that this binary categorical vector depends on altitude. And I say that the family is binomial. And here's my data set. All right, so now let's go ahead and let's visualize our actual model. Well, I'm going to go ahead and take a look. All right, so here is the transpose of the model, or of the box plots we just looked at. And so we can see this is really just the same box plot that we saw before, but now I turned it over. Why did I turn it over this way? Because altitude is our predictor and the presence or lack thereof of the species is our target variable. Okay, so here we can see a little bit more precisely what the box plots look like. And, so you see the same thing. And here's the actual curve for our model that we can see that, when we're at low altitude, we expect to not see the species at all. When we're at high altitude, we expect it to be more likely to come across the species. All right, and so this is really just logistic regression. In another format, it's fitted slightly differently, but it's mainly, you'll get pretty much the same thing if you run the GLM function. All right, and here's the coefficients. So this is going to be fitting log odds because that's what we put in for the binomial distribution. And here's the summary of it, and we can take a look and kind of evaluate our model. We can look at the log likelihood and the deviance and the number of iterations. All right, so a good thing to know when you're building models, if it takes a long time to fit a model, if it takes a lot of iterations or it takes a lot of computation time compared to other models, structures, then you probably have a bad model structure. That's just a good rule of thumb. So if your data really is like saying like two different things and your model and your computations can't converge because it's bouncing between the two different signals, then you'll notice that the iterations can be quite large. Whenever it takes a large number of iterations or it takes a long computational time, just be ready for your model to be crap. Something I kind of learned the hard way. All right, so now what we want to do, we want to build a model for two different species. Now, remember, I've got categorical data. And if I have two different species, I could either have both species at once, I could have one or the one species but not the other, I could have the other but not the first, or I could have neither. There's 4 possibilities. So if I want to do this technically correctly, I actually need 4 different situations to be in. Okay, so how this package and this function handles this is that I need a different column for each one of the situations. So I have 4 different possibilities. I need 4 different columns. All right, so when I have neither, both of these are equal to 0. When I have only one, then this one is 0 and this is present. When I have this but not this one, and so on. So what this will be when I have neither, then this is going to be yeah. So if I don't have either species, then this is 0, that's 0, which means this parenthesis is 1. This parenthesis is 1. 1 times 1 is 1. And if you go through and work this out, I capture all the different possibilities. Okay, so now when I build this, you'll notice I've got C bind, and I've got neither, or the one plant species, the other plant species, or both. Now here's something kind of funny, is that this package likes to smooth things out. And I took this example from the package examples. So if you load this package into your computer and you go into the library, this code that I base this off of will be there. And the author chose degrees of freedom of 1.5 for the smoothing. I just went with it because it was there. That might be good, might be bad. I don't know. If you have the lower number you have, the more like stiff your lines will be. The greater the number, the more wiggly your model will end up being. And I'll explain what wiggly means in a moment. And then here we got binomial 2. And let's take a look at our model. All right, so here is our deviance, our log likelihood. Okay, so what's going on here? Remember, I've got 4 possibilities. What this is doing, this is building actually 4 minus 1, 3 logistic regression models. It builds a logistic regression model for the first possibility, and it builds a logistic regression model for the, let's see, it's going to be the first or the second. Then it's going to build a logistic regression model for the first, second, or third possibility. And so there's a total of 3 different models. And then what it does, it gets the probabilities from these. And you notice how I add the, I combine the different vectors. It gets the probabilities and does subtraction to figure out what the actual probabilities are. And so these models get rather complicated. So for right now, we're just, just look at the output, enjoy it, and we'll get digging into this later. All right, so now what I'm going to do after I get this, I take a quick look at the output. So you can see that, like here, the p-value is telling me not a very good model right there. But here it's okay. So this is a pretty complicated model. I would honestly start digging in, start reducing some stuff down if I was doing this for work for real life. But for now, let's just keep it simple. All right, so I'm going to make my predictions. We use the predict function, and you'll notice that here I put in response. If I don't put response, it's going to by default give me log odds because that's what's coming out of logistic regression. All right, I want response. Response means give me the probabilities. That's why I actually want the probability. I do not want the log odds. And here I'm just reshaping things so that I can go through and model, or I can make a visualization of what's going on. So down here, I go through and I just visualize the output of the model. Okay, so here is the actual predicted values across the range of values of altitude. So the situation where I have both species is green, so that's pretty rare. That's always the lowest. And then neither looks like it's in the middle pretty consistently. And then this species only is the red. And then this species only is this teal color. All right, so we can see that most of the time I'm only going to get one species present. And I'm not going to get zero, and I'm not going to get two of them. I'm going to get one of them. And so the species is the most likely event at these lower altitudes to see this species alone and not the other one. At the greater altitudes, I'm more likely to see this species by itself. And as I go uphill more and more, I would expect to see the other species less and less. All right, so let's kick it up a notch. Let's say that I want to know at any given location, at any given altitude, what is the most likely species to encounter? Okay, so what I'm going to do, I'm going to make the assumption that in a surveyed area, I can only have one species. Now, we looked at the model, we looked at the data previously, and we know that that is not correct. But in statistics, sometimes I just proceed to work with it. If I look through, I have a lot of columns. I have a lot of target variables. If I want to, partition this up into situations of, this variable or this variable or this variable, two or more, three or more, four or more, it's not going to really be feasible. I'm not even going to be able to understand it. So technically, this is correct. This is mathematically wrong, but this is still a good way to get insight into what's going on. So what we're going to do, I'm going to model the situation that I can only have one species in a surveyed area, even though the data contradicts that. This is an assumption I'm going to make. And I want to know at a given altitude, what is the most likely species to come across? All right, so I'm taking all of my target variable names, I'm putting it in the cbind statement, and I'm saying it depends on altitude inside the smoothing function. Now, something that's important here is that you notice I have multiple levels to my categorical data for this. I'm using family multinomial. This is important. Okay, now there's going to be problems with this. There are some issues with computing this. Yeah, that's how it's going to be. But we know we're doing something wonky anyway. And so this is just telling me that something might be off. I think what's going on is that either we have more than one in a row, or we have no ones in a row is what's causing this. So now let's go ahead and take a look. So I go ahead and I make a prediction on each of the different altitude values. So this will give me my fitted values. Now, something about the VGAM package, it doesn't give me a data frame by default, and data frames are really the format that it's easiest to work with in R. So I go ahead and I convert it to a data frame. And remember, response gives me the actual probabilities. If I don't do that, I'll get log likelihoods. Okay, now something I want to point out, notice that if I do row sums on my predictions, so what this does, this spits out a matrix where each altitude corresponds to a row, and each species is a column, and inside the entries is the probability of seeing only that species at that given altitude. Okay, so if I do row sums and everything adds up to 1, then I can see that, what this is saying is that there is exactly one species at each given surveyed location. And that makes sense if I survey a small enough area, by the way. Yeah, if I survey a small enough area and we have like a competitive system between species, which makes sense in ecology. All right, so now let's go ahead and visualize this. All right, so I can see that, first of all, it's a lot. There are a lot of predictor variables in here. We can see that this green one, is like in the middle range, is likely to be encountered. These two become more and more likely as you go uphill. They'll probably become like a 50-50 if we were to keep on going uphill higher and higher and higher until the species couldn't grow at that high of an elevation. And here, like this blue, we know that's a pretty rare species to come across compared to the others, according to this model. Now, what if I want to reduce this down to just 3 species? Okay, there's a catch to this. I have to be aware of the fact that if I have like all zeros, if I was to reduce it down to just 3 species like I'm doing here, I have to consider the fact that this modeling structure makes the assumption that there's a 1 in my target variables on each row somewhere. So what I have to do, I have to create a column that whenever these 3 species are not present, that this one will be a 1. Otherwise, the system won't run. So if I'm interested only in these 3 species, I could have this species, or this species, or this, or none of them. Or it could be another species altogether, or no plants at all. That's a possibility. Okay, so what I want to do, I want to create another column that whenever it's a 1, we know that these 3 were not present. Another species may be present, or no plants were present at all. If I don't do this, the model will not run. And so then here I'm just running the model. And you notice I'm using cbind, and I have to include other. All of my rows of target variables have to add up to 1 for this. And you'll notice that if I do row sums, it always adds up to 1. And now we can see a little bit more clearly what's going on with these species. It's easier to, now this modeling structure makes the assumption that it's either these 3 or nothing, or some other species altogether. And you'll notice that my probabilities are larger, or excuse me, my likelihoods are larger in this scenario. All right, well, that's all I've got for you. Take care and goodbye.